And if somebody told them there's such a thing as a chapter, the only way we discover that level of meaning in the genetic material is this thing called context richness. Now, context richness is the same thing, you see, as this embedding or nesting we just saw the animation about. So when you saw that short wave, which is an ultraviolet wave, which is the helix of DNA, that is in fact what your genetic engineer now thinks he understands. He thinks he understands how one code sits next to the other in this simple slinky, which is useful, but it's only the very beginning. Because in fact, what happens is that now you take this sequence of a certain series of codons in this little slinky, and you take this and you braid it into an envelope where the wave fits in this lovely little envelope. And you have an envelope on an envelope on an envelope. It's like saying, oh, the answer lies folded in an envelope. But that's easy to understand, because if you took thread and then you kind of braided it, you might have string. And then if you braided that string, you'd have a rope. And then if you braided that rope, you'd have a very fat rope. Now, if you were done, you'd have a wave the length of that very fat rope, which is a very long wave, which contains the wave of the string and the wave of the thread. But yet, if you were debugging where that rope is going, you couldn't get a clue about the meaning of the long wave by looking at just the letters, the short wave, the thread. The point is that the way Mother Nature decodes DNA is, here you have this sequence. It's like genetic material is lumped into these groups for a very important reason. It has to do with, like, the way you decode DNA is because after it's braided into the rope, the actual waves that are tucked inside do not get mechanical access to the RNA. So mechanically what's happening is the DNA, the deoxyribonucleic acid, is able to share its templates, its codons, its cookie cutters, so the half helix can say, okay, waltz in here, RNA, and mate to see if these two things fit together. That can't even begin to happen unless mechanically the DNA has access to the RNA. So from a mechanical point of view, if you're some of the DNA and you're tucked inside the thick, fat rope, you don't have access to the RNA. So guess what's happening? That particular section of code does not get read. And so, in fact, whatever mechanically does this long wave braiding in your DNA is what's called switching the active sites. The programmer. So in fact, what the genetic material has a way of deciding what groups of codes do in fact replicate. Now this has been a mystery to genetic engineers for a long time, that even in fact, say in the cases of AIDS, where you have this virus and it's there in your cell, but it appears to be dormant. And then suddenly, if you get a cold or you get depressed, and in fact, if you get depressed, you're more likely to get a cold, and then suddenly your immune system is weakened, and then this virus switches on. So what they didn't understand is, mechanically, what is the way in which a group of code is switched on? It's just like you're waltzing up this little ladder of your DNA, and because of the braid, the DNA knows read 2, skip 4, read 6, skip 4, read 2, skip 6. Now, the way that's done is the braiding. But if you're this simple mechanical engineer that has made simply a map of which codon is next to each other, knows the letters, but doesn't know the words or the paragraphs, or the context, or the syntax, then you're in big trouble, because in fact, you don't know how certain sequences of the codes are in fact deciding to replicate. Now, the really fun part of this little story that I'd like to get to, I call it the storal to the mori, which is a funny way of saying the moral to the story, is that it might just be that your emotion, this mechanical sound wave, this long wave that comes from your EKG, is in fact the way in which your DNA gets braided. See, we already know that genetic material has to have a way of making groups switched on and off. And we suspect that's what's called stoichiochemic or stoichiochemical or structure related or simply shape related. So we're not going to get to the clue of which groups of codes in DNA get switched on and off by simply looking at which little codons are in a row. We're going to have to look at the long wave structure. The long wave structure, as we just saw from the braiding animation, is in fact an image of how sound waves, or very long, it's called phonon, which is just a name for sound in a liquid. So you have these sound waves or phonon waves, in fact, mechanically braiding your DNA. I hypothesized this, or suggested this as a theory, many years ago. I was working with the Heart Math Institute in California, and I wrote a chapter. It's also on my website at danwinter.com, and the chapter was called "Braiding DNA is Emotion the Weaver." The actual link to this is at danwinter.com/magneticx. And in that book, in that little story there, what I suggested was that emotion may be the weaver of this pattern, this long wave structure in your DNA. Well, we had these long conversations at the Heart Math Institute, and at that point there was a scientist there named Glenn Ryan who did an experiment based on the hypothesis at my suggestion. And the experiment he did was very simple. What he did is, when the DNA slinky or helix splits or replicates, there is an enzyme that's associated with how much glue or how much bonding has happened at what I call the zipper down the center of your DNA. The zipper is where the actual nonlinear hydrogen bond at the two halves of the codon break and mate each time. And that zipper is associated with a very particular enzyme. And all Glenn Ryan did was measure for the presence of that enzyme during DNA replication, splitting and recombining. And what he found was very profound, and we, with his permission, reprinted the paper that was published in the ISSEM, the International Society for the Study of Energy magazine. And the article is reprinted at danwinter.com/Rhine. That's R-E-I-N. And what he found, to summarize very simply, was that the presence of the enzyme that makes the slinky bond and unbond, that actually is the zipper, you could say. The presence of that enzyme varied dramatically with the amount of musical coherence in the heart. So here you have this heart harmonics, the heart sounds, actually affecting how tightly the DNA slinky was doing the braiding. And look what happens when you braid the slinky. You get this lovely little nest of donuts, okay? You get a nest on a nest. Well, the slinky doing this in your DNA happens mechanically, directly, measurably, in response to the orderliness of the sound harmonics coming from the heart. So let's take a little break here and we'll switch to some images of that. We wanted to just make the point that if we look at the harmonics in the heart at moments of intense emotion, we do in fact see these lovely cascades here. This is a biofeedback device we're working with that I invented called the HeartLink, and we'll have a new version soon. But what we do is we take the heart voltage here, the EKG or ECG, and we analyze the music coming from the heart between 0 and 20 cycles, and we see this cascade, very similar to what we saw in brain waves, alpha, theta, and delta, same bandwidth. But then, what we see is when the great amount of coherence or music does come from the EKG dynamically, if we take the second order frequency signature, FFT, called septrum, we see that the space between harmonics is 1 over the golden mean ratio, 0.62. So, in fact, the space between these harmonics here is 1.618, as close as we can measure, which is the golden mean ratio. So, it appears that this interstitial spacing between harmonics is generating a cascade musically in the heart, which is very coherent. And in fact, we believe that if we